Hello everyone, I am Rohan. I am a graduate student in the Department of Computer Science. I am here to present deep learning for natural gas reservoir. This is a joint work between Rice University and Park Energy. I see all of my collaborators here. Hi. So to advance, to motivate the talk, what we trying to solve in this problem is, let's say we have a huge natural gas reservoir which consists of multiple wells. And each one of these wells has different characteristics of itself. We can think of the well as an input-output system, where the outputs may be the items of our interest, for example, the flows and the various pressures in the east well. The inputs may be the external factors that act on the reservoir and changes its state. So for example, this can be the plunger values. I'm going to talk a little bit more into details of plunger values later in the future. But for now, it can be thought of as inputs that change the current state of the reservoir. So what we want to do is to build a model. We want to build a deep learning model to model this input-output behavior of the reservoirs. So the question to ask naturally would be, why would you even need this model? So it's a standard knowledge that the output of a reservoir would decline over time. And one interesting question to ask would be, what is the current value of a reservoir at a current point in the time? So if we can model it correctly, we can predict the values of the outputs in the future, and then we can access directly the value of the reservoir at that timestamp. So that is the prediction problem. And then there is another problem that we can solve while managing the modeling the reservoir, is to manage the problem. Manage the reservoir. So we can think, after we have modeled it as input-output function, so that we can verify we can change the inputs or the plunger values that I have talked about to maximize the production from the entire reservoir. So here we are not modeling a single well at a time. So we are considering the entire reservoir as an evolving system. So we are even taking into account the physical communications between the wells as well as their correlations between them. So it's tending to be a hard problem, and we can see why from a plot like this. So this plot is extracted from one output flow rate of one of the wells from one of the data set that we have. And this is normalized rate flow. So it has therefore it has a mean 0, and it is capped at standard deviation of 3. So you can see here that the values fluctuate a lot, right? And I don't need to probably convince you to convince you that this is a hard thing to approximate or to even model this problem. And here we can see that there are some very high fluctuations. And we probably think that this might be because of the external inputs, like the plungers, taking effect at these timestamps, so that the values has changed drastically from this time to that time. Now, I will go a little bit into plungers in case you do not have background on this. This is what I described as the input to the reservoir that comes in. So in general, when a reservoir first starts to perform, it is free of all debris, and it can produce in its own differential pressure at a high rate. However, with time, there is accumulation of there is liquid fallback. So there is accumulation of debris, and slug forms in, which causes the liquid pressure to go down, and the production drops. And then at some point, it totally clogs the system in producing any more natural gas. So what happens? We use something called a plunger. Plunger is basically something like a piston, and that goes up and down in number of cycles to clean the well of this slug. And finally, what we have is a system that again comes back probably to the somewhere very near to the initial state, and it again produces in a higher differential pressure. So taking a look back into the graph that I showed before, here we have said that these values, the drastic changes, may be because of a plunger. But there might be more things that goes on in this picture. Since the values are so erratic, it might be because that there are many other factors in the reservoir which are actually contributing to this nature of the well. For example, it might be the effect of other plungers in the vicinity, or it may be because of the correlation between the different wells. So the long-term trend shows that this might be because of other factors, and we would like to model all of these factors together. So let's take a look into what the state of the art tries to do in solving this problem. So a state of the art would probably fit something like an exponential or hyperbolic curve to this data set and try to predict the values in the future given this model of the exponential of the hyperbolic decline curve. Obviously, this will ignore a lot of important factors that we already talked about, which might affect a lot on this in this well behavior. For example, the plunger characteristics, which are the inputs to the well. And if we are optimizing on a single well, we are having a limited observation on time interval. So we are not taking into account a lot of other factors, as well as we are not taking into account the communication and correlation, which might play a lot of role in predicting the future behavior of these wells. So the question to ask is, can we do better? And our answer is yes. We would fit a neural network to this system and model the input-output relationship so that we can model the outputs better. To go before going into the neural network model, we would first formalize the problem, define the variables, and then go into the details. So the inputs that we talked about for the plungers can be thought of as x's to the data, and it is capped. This is variable at every time instant t, and each one of the t has the ith plunger, or if the reservoir is consisting of n number of plungers, then I will range from 1 to n. And each one of them is a 4-dimensional vector, which consists of the different factors that the plunger characteristics are dependent on. As I said, xt is a vector consisting of all the different plungers in the reservoir. Similarly, we can define zt. Zt is the instantaneous state, which corresponds to a different characteristics like the flow rate and the pressures in the well. And these are, we will see all these variables later as well, so we can know how this affects our system. The instantaneous state again is another vector which consists of 5 different dimensions we are interested in. And again, this zt is again is accumulation of all the different wells in the reservoir. Similarly, this is our output, which is the dimension we are interested in. This gives us the flow rate at particular time for some particular well I. And this is again a vector of with dimensionality will be the number of wells. So we have seen z's and t, which are looks a bit similar. We will define why these are defined differently and see how they affect the reservoir system. So what is the goal of our training? Given a very large set of historical xt, zt, and yt, which we classify as our training data, we would like to train our model on this data. And given the x's and z's at the future timestamp, we would like to predict the y's later, right? So we will start building the intuition for our model. And the model first takes in the input as the last few observations from the testing data set, which corresponds to the z's. So these are the instantaneous state of the reservoir for every well, for every timestamp till n times before what we are interested in. And this is shown here, the entire dimension. And this goes to the becomes a neural network and goes to initialize the initial state of the reservoir. So if you're interested in the neural network architecture, this is a fully connected layer which encodes all of this information and converts them to the initial state of the reservoir. Going forward, this reservoir state is used to initialize the state, and this recursively goes forward to predict even further reservoir states in the future. And here we will take into account the inputs, which are the plungers in our case, and then we will use them to predict the flows at every timestamp in the reservoir state. Now, if you're interested again in the neural network architecture, these plungers are again encoded by a fully connected layer. These flow rates are available to us from a decoder layer, and the reservoirs are an instance of a recurrent neural network which models any time series. So if we look into the entire architecture in a bit more detail, what we see here is the encoder, which takes into account all the previous instances of the instantaneous values of a reservoir till n timestamps before what we're interested in, plugs it into a fully connected layer, encodes for us the initial state of the recurrent network. So the recurrent network is unrolled here for elaboration purposes. And the plunger encoder takes in the inputs, and we get the output decoder, and at every timestamp we get the outputs. So the recurrent network that we have implemented here is a multi-layer LSTM cell. If you're interested in LSTM is a variation of a recurrent neural network, which has several other knobs which modify its state. For example, there is something called forget bias, which lets the network forget some of its past information, and it's essentially easier to train. So during training, we fix the x's, z's, and the t's, so all of these values are fixed, and we learn every color-coded variables in the network. And during the testing phase, while using all these learned parameters for the networks, we plug in the new z's and the x's and predict the y's. So let's take a look into what are the data set that we used. We collected plunger and flow values for our reservoir in Texas, which consist of around 5,000 wells. The total length of our data set was around 1 year. We discretized the data in a period of 1 hour. And there are 4 plunger dimensions we considered as our input. The feature of prediction we are interested in was the rate flow. And the instantaneous features which were input to the encoder were of dimension 85. We trained our neural model. We coded it up in TensorFlow, and we used Amazon Web Service GPU machine, and it took around 2 hours to train on this on this system. Now to note here, like the current system that we have trains on the entire reservoir system and predicts the performance, and is optimized to predict the performance of a single well. So this current system that we have needs to be run around 4,789 times to get the entire prediction for all of the wells in the reservoir. So as part of our future work, we would like to encode this up in a single LSTM network, so that we can predict all of the flows in a single in a single training time. So going into the results section. So the first experiment that we do here is we use the trained model to predict 90 days into the future from one starting point, and we like to see the performance, how our neural model does. So ideally, we would like to see that the entire prediction matches with the actual target. And for our baseline comparison, we use the exponential and hyperbolic curve fitting. So this is one result from one of the wells, and it's shown in 90 days in advance from our starting point. And we see that the target here is in the blue, whereas our model has prediction which is shown in green, and it's has done a good job in predicting the performance. The red and blue, the light blue shows the curve fitting lines. It's a bit hard to see because mostly they are overlapping each other. It's probably easy to identify that they have overfitted the flow. And our model has correctly matched the spikes. So we believe this is because it has correctly understood where the plunger operations have been, and that's why it has correctly classified each point and the spikes correctly. However, there are some points where our model has predicted a low value, whereas the original value was high up. So however, we see that the period was probably continuous for our case, and we believe that this might be because of sensor reading error in the training data and in the test data, and probably this is like a bad data example. Now there is another interesting test that we did, which was one of the focus of our work, which was to see how our model does while taking into account the whole picture of the reservoir compared to a single well. So here again, we try to predict 90 days into the future, taking a few initial days as our input. And we plot the L2 loss, or the L2 loss with time. And ideally, what we would expect is to have a 0 error, right? But probably what we can expect is to have a low error in the initial few days and the error to increase further ahead. So we have compared this result using two of our, using like the two inputs that we talked about before, the inputs that are only local to a single well, whereas we also use the inputs that are global to all of the variables in the reservoir, like using all the plungers and all the instantaneous values for the entire reservoir system. So the graph that we show here, the blue one shows the well-specific training, whereas the reservoir shows the orange is the reservoir training. In the test data, we see that the error for the well-specific training increases with time in 90 days, in the 90 days period, whereas the reservoir more or less does a better job in staying constant. We would expect that this would go up somewhere further in the future, but probably our argument that the reservoir setting was was giving in more information for more correct prediction was accurate. That can be seen from this test data. Sorry, the test result. And here is another well. Here we see that the target was in the as usual it's in the blue, and our green is the prediction characteristic. We see that our model has correctly classified the spikes in the lower flow spikes, but has missed accurately predicting the top flows. So we would like to analyze more on this. We have not done this till yet. As part of future work, we would like to see why this is being the characteristic. And here also we can see that the reservoir, taking into account more inputs from the reservoir, helps in getting a lower accuracy compared to a well-specific training. So as part of future work, what we would like to do, we would like to test our model on more reservoirs from more data set. We would like to use our model to optimize reservoir management, so that we can use our model to find the correct plunger value, so that we can use it to better productivity from the entire reservoir system. We also would like to transfer knowledge from one trained model from one particular reservoir and test it on a new reservoir where we do not have that much of training data, but see how it does in testing characteristics. Also in this work, we have not taken into account any of the geographical features which might be very crucial in understanding the correlation between the well, and we would also like to take into account those additional information. With that, thank you for your attention, and I would be open to questions.
We have time for a question or two, and then we'll be breaking for lunch after that.
So what is the reason for separating the X and Z inputs, even though both are inputs of time?
Sure. So, so the item of interest that we would like to predict is the flow rate. And there are other characteristics, for example, like the pressure in the wells, which are important while we try to encode the information for the reservoir. But that is not something we are trying to predict. So that's what Z is. So Z is, so Y is a subset of what Z is. And these are the instances from the previous timestamps that we are giving to the encoder.